Welcome to this video, the gradient and the tangent plane. In this video, we're going to look at surfaces in 3 dimensions and tangent planes to that surface, and also use this sort of setup to approximate values of functions at various points. The computer programs used for graphics and other things for this particular video are available in text form in the YouTube description of this video. The goals of this video are to discuss the gradient of a function capital F of x, y, z, 3 variables. For a given constant c value, scalar c, let S be the surface given by f of x, y, z equals that number c. Let's use Sage Math to display that surface and also to display normal vectors to that surface. Also, for a given c value, determine the equation of a tangent plane to a surface f of x, y, z equals c at a point on that surface. Let's define what it means for a function of 3 variables to be differentiable. Let's find the tangent plane to a surface at a given point on that surface. And knowing the value of f at the point x0, y0, z0, approximate the value of f of x, y, z, where x, y, and z are sufficiently close to x0, y0, and z0 for this approximation to be effective. Also, let's suppose for a 2-variable function, suppose z equals little f of x, y represents a surface, represents a curve on the surface S, and it satisfies f of x0, y0 equals z0. Let's approximate the value of z, which is going to be f of the values x and y, for values of x and y near x0, y0. And that is basically the sort of thing that we're going to do in this video. So why are we going to do this? Well, it's a good application of multivariable calculus, calculus of functions of more than one variable. It can be used to approximate the value of function little f of x, y when the values of x and y just slightly change from other values. Also, for a 3-variable function, capital F of x, y, and z, want to approximate the value of f of x, y, z when you just change the values of x, y, and z just a little bit. And we will have nice graphics for these sorts of things. It's nice to write programs for this, and it's also fun. So let's talk about the equation of a plane. Let's suppose that we want to find the equation of a plane P, which has the following properties. It contains the point x0, y0, z0, which is down here in the plane, and it has a normal vector n perpendicular to that plane P. P is this plane. And let's suppose that the components of n are the numbers a, b, and c. So what we want to do then is to find out what equation this triple x, y, and z must satisfy. So here's a picture that we saw before. We have this plane P. We have a point x0, y0, z0 in that plane. We have a normal n to that plane. And we have a point, an arbitrary point x, y, z somewhere in that plane. So as we said before, we'll let n be the normal to that surface, an orthogonal vector orthogonal to that surface. And let's let v be the vector going from x0, y0, z0 to this point x, y, z. So the components of that vector are x minus x0, y minus y0, z minus z0. In that case, the vector n and this vector v are perpendicular. And that tells us that the dot product of those 2 perpendicular vectors has to be 0. So what does that mean? It means the vector n, which has components a, b, c, times the vector v, which is this stuff, equals 0. Now let's remember how we take the dot product of 2 vectors. It's this component times this component plus the second component times the second component here, plus the third component times the third component here. So this vector equation can be rewritten as a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0. So this is one way that we can write the equation of that plane. So let's see what we can do with this as an example. Let's find the equation of the plane containing the point 1, 3, minus 2. That's basically the x naught, y naught, z naught here. And perpendicular to this vector, 6, 2, minus 3. We can say that this plane is perpendicular to this vector, or equivalently, we could say that this vector is perpendicular to this plane. So let's see how we can solve this. Our solution is first, here's the equation of the plane that we saw before in a general form. And a, b, and c, according to this, the components of our normal vector are 6, 2, and minus 3. The x naught, y naught, and z naught values are the values of this point here, which is 1 minus 3, 2. So what we'll have in that case is this will be x minus 1. This part right here will be x plus 3. X minus a minus 3 is x plus, y plus 3, sorry, y. Minus, and then here we'll have z minus 2. So we substitute in the values of a, b, and c, and also the values of x naught, y naught, and z naught into that equation. So here is the equation of that plane. So let's use MATLAB or Octave to get a surface plot for this equation that we just saw. 6x plus 2y minus 3z plus 6 equals 0. The first thing we'll do is solve this for z. And if we do that, we'll find out that z is 2x plus 2/3 y plus 2. And to plot this surface, we can use this MATLAB or Octave program. It should work both in MATLAB and Octave. So first we just have a comment that that's what we're going to do. We're going to clear the workspace, basically clear almost everything, close all the figures, and then we're going to let x be an array that goes from minus 8 to 8. Its elements go from minus 8 to 8, and there are 32 equally spaced elements in there. So this basically are numbers that we could have on our x-axis. Similarly, y will be an array containing numbers from minus 8 to 8, and there will be 32 equally spaced numbers starting with minus 8 and ending with 8, ascending. We'll let xy be meshgrid x comma y. Notice we have capital letters here, lowercase letters here. The lowercase x and y were defined to be these arrays up here. And there's another video that I made that shows you how to use meshgrid, mesh, and surf. So you can refer to those. So in any case, now we'll just let z, capital Z, be 2 times capital X plus 2/3 times capital Y plus 2, which is the equation that we have up here. And then we'll graph the surface for those points having x, y, and z coordinates given by this. And we'll, for put in hidden off, probably don't need that. That was because of another program that was run earlier, I guess. Set alpha to 0.5. This probably works in MATLAB, but I don't think it's implemented in Octave yet. And this is just a comment. It was another command that I tried, commented it out. When we execute this code, actually using Octave, this is the output. The x-axis and the y-axis looks like go from minus 10 to 10. That means that I must have changed these two numbers to go from minus 10 to 10 instead of minus 8 to 8. Didn't notice I did that. Don't remember I did that. But in any case, here is that plane. We can write the general form of any plane in 3 dimensions as a constant a times x plus b times y plus c times z plus d equals 0. So if you see any equation that fits this form, we should automatically, very quickly recognize it as being a plane. We also saw before that the equation of a plane containing the point x naught, y naught, z naught can be written as a times x minus x naught plus b times y minus y naught plus c times z minus z naught. Any choice of a, b, and c will give us a plane containing this point, because x minus x naught will be 0, y minus y naught will be 0, and z minus z naught will be 0 when x, y, and z are x naught, y naught, z naught. So basically any plane going through x naught, y naught, z naught can be written in this form. So now let's move on to differentiable functions. We're going to be looking at differentiable functions of more than one variable. For functions of more than one variable, differentiable does not mean has a derivative. It's a little bit more complicated than that. So things change when you have more than one variable. For a function of one variable, differentiable did mean it had a derivative. But for functions of two or more variables, we have to change our definition a little bit so that it's more useful for what we're going to do. So let's talk about differentiable functions of several variables. A function f, capital F of x, y, z, is differentiable at the point x naught, y naught, z naught if the following equation holds. F of x naught plus delta x, y naught plus delta y, z naught plus delta z is equal to f of x naught, y naught, z naught plus the partial derivative of f with respect to x at x naught, y naught, z naught plus the partial of f with respect to y at that point times delta y plus the partial derivative of f with respect to z at that point times delta z plus epsilon 1 times delta x plus epsilon sub 2 times delta y plus epsilon sub 3 times delta z. And these epsilons have to satisfy the following property. Epsilon 1 goes to 0, epsilon sub 2 goes to 0, and epsilon sub 3 goes to 0 as delta x, delta y, and delta z all go to 0. In this equation, we think of each of these epsilons as being a function possibly of x, y, z, delta x, delta y, and delta z. Turns out that if this function is differentiable at this point, then this surface f of x, y, z equals c has a tangent plane containing that point x naught, y naught, z naught. So differentiable implies has a tangent plane. Also, this equation up here can be rewritten in the following form. If we let x minus x naught be the delta x that you see here, y minus y naught be delta y, z minus z naught be delta z, then f of x, y, z can be written just straight from up here in this form here. And we still have to have epsilon 1, epsilon 2, epsilon 3 going to 0. But in this case, it will be as x minus x naught goes to 0, y minus y naught goes to 0, and z minus z naught approaches 0. Notice that we're talking about limits here. The limit of these things is going to be 0 when the limit of these three things is going to 0. The limits approach 0. X minus x naught going to 0, for instance, just means that x gets closer and closer to x naught. Similarly for the y's and the z's. But how can we tell if a function is differentiable? Well, let's look at a fact that will at least cover most of the situations that we will encounter, and another fact also. So two facts about differentiability. If we have these two things holding, the partials f sub x, f sub y, f sub z are defined inside an open box containing the point x naught, y naught, z naught, rectangular box, and if these three partial derivatives are continuous at the point x0, y0, z0. So we have to have continuity of the derivatives at this point and the derivatives existing inside this box, but elsewhere, not necessarily continuous. Then we can conclude that f is differentiable at x0, y0, z0, and we can write down an approximation formula. F of x0 plus delta x, y0 plus delta y, z0 plus delta z is approximately equal to f of x0, y0, z0 plus this partial derivative with respect to x at that point times delta x plus the partial of f with respect to y at that point times delta y plus the partial of f with respect to z at that point times delta z. So we're evaluating the function and its three derivatives at that point x0, y0, z0. And this is true as a good approximation if delta x, delta y, and delta z are sufficiently small. So what can we do? First of all, let's start with the definition of f of x, y, z being differentiable. So basically we have these terms over here plus 3 epsilon terms, and we know that as x approaches x0, y approaches y0, and z approaches z0, then this factor of epsilon 1 goes to 0, the factor of epsilon 2 goes to 0, and so does epsilon sub 3. So we can talk about the tangent plane approximation of f centered at x0, y0, z0 by just eliminating these little epsilon terms here. So we'll define L of xy to be just what we have up here without these small corrections. So L of xyz is equal to f of x0, y0, z0 plus a partial of f with respect to x at x0, y0, z0 times x minus x0, similar term involving the partial derivative of f with respect to y, and a similar term involving the partial derivative of f with respect to z. So in that case, what we can say is that f of xyz is approximately equal to L of xyz for x sufficiently close to x0, y sufficiently close to y0, and z sufficiently close to z0. We could also write it this way: f of x0 plus delta x, y0 plus delta y, z0 plus delta z is approximately L of x0 plus delta x, y0 plus delta y, z0 plus delta z, and then that would be equal to, just using this formula up here, where this factor would just be delta x, this factor would be delta y, and this factor would be delta z. We have f at this point plus the partial of f with respect to x at that point times delta x plus the partial of f with respect to y at that point times delta y plus the partial of f with respect to z at that point times delta z. So the linear approximation of f, L of xy, we saw could be written as f of x0, y0 plus the partial of f with respect to x at x0, y0 times x minus x0 plus the partial of f with respect to y at x0, y0 times y minus y0. Well, if we look at these terms up here in blue, we can write this sum, this term plus this term over here, as the dot product of two vectors. The vector whose two components are this and this, dotted with the vector of two components, which is this vector here and this vector here. So L of xy can be written as f of this stuff plus this stuff dotted with this stuff, the dot product of two-dimensional vectors. Well, this first part right here, this first vector, the partial of f with respect to x, the partial of f with respect to y as the two components, is called the gradient of f. And we're evaluating it at the point x0, y0. So we have the gradient of f at this point dotted with this vector. Another way that the gradient of f is written is by this symbol right here. This represents the gradient of f at the point x0, y0. Let's recall a couple things about the dot product of two vectors, also called the scalar product because the dot product of two vectors is a number, a scalar, real or complex, in our case real. First of all, here's the definition. If a and b are vectors, the dot product a dot b is identically equal to this. This is the vector a component-wise, here's the vector b component-wise, and the dot product is a1 times b1 plus a2 times b2 plus a3 times b3. a1, a2, a3 are just real numbers, b1, b2, b3 are real numbers, and so this sum of products is a real number. Now you might wonder why we do something like this. Hopefully you remember. Suppose we have two vectors a and b and there's an angle theta between them. Then it turns out that the dot product of a and b is equal to the length of a times the length of b times the cosine of the angle between them. So let's talk about the gradient of a function. The gradient of f evaluated at the point x0, y0, z0 is the following vector. The first component is the partial derivative of f with respect to x at x0, y0, z0. Second component involves the partial derivative with respect to y of f at that same point. And the third component involves the partial derivative of f with respect to z. So there are three components of this vector. When we evaluate these partial derivatives at x0, y0, z0 in each case, this vector consists of three components, all of which are real numbers. The gradient of f can also be written this way, the gradient of f, using this symbol to represent the gradient of f. You don't really need parentheses here. You can write the two together like this, and that's just what we call the gradient of f up here. So these are a couple more notations for the gradient. F in this case is a scalar valued function. F of x, y, z is a number, but the gradient of f, as we can see from up here, is a vector valued function. When you evaluate the gradient of f at a point in 3 space, you get a vector with 3 components. Let's recall this formula for the tangent plane. Let's use it to solve a problem. Let's let f of x, y, z be x squared plus y squared plus 1/4 z squared. Note that if we plug 1, 3, minus 2 in for x, y, z, the value of the function turns out to be 1 plus 9 plus 1, which is 11. So for part A, let's find the equation of the tangent plane to this surface. This stuff equals 11 that we had up here at the point 1, 3, minus 2. We just calculated the fact that 1, 3, minus 2 is on this plane when we have an 11 here as the constant. Part B, let's use that tangent plane approximation to estimate c when x equals 0.9 and y equals 3.02. So for our solution to part A, we start with x squared plus y squared plus 1/4 z squared equals 11. And this on the left side is our function f of x, y, z. So the gradient of f at x, y, z is what? Well, the partial of this stuff with respect to x is 2x. The partial derivative of this stuff with respect to y is 2y. The partial derivative of this stuff with respect to z is 1/2 z, z over 2. Now let's evaluate that gradient of f at 1, 3, minus 2. So substituting x equals 1, y equals 3, and z equals minus 2 into this formula up here, we get 2 times 1, 2 times 3, and minus 2 over 2. which simplifies to the vector 2, 6, minus 1. So now for the tangent plane, that's going to be the gradient of f at this point of tangency times x minus 1, y minus 3, z minus a minus 2, which is z plus 2. So this gradient dotted with this vector equals 0. That tells us that this vector and this vector are perpendicular. But in any case, continuing, the gradient of f is this vector multiplied by this second vector equals 0. Using the component-wise definition of a dot product, this is going to be 2 times x minus 1 plus 6 times y minus 3 plus minus 1 times z plus 2 equals 0, and that's what we have down here. Doing a little bit of algebra, we can simplify this to 2x plus 6y minus z minus 22 equals 0. So this is the solution to part A. This is the tangent plane to that surface at that point 1, 3, minus 2. So now we move on to part B. Let's use this tangent plane approximation to estimate z when x and y are these numbers. So if we look at the tangent plane equation down here, we can solve this for z in terms of x and y. What we get is z equals 2x plus 6y minus 22. Plugging in x is 0.9 and y is 3.02. Our approximation for z then is this stuff, which when you multiply it out and add, gives you minus 2.0800. Notice that this calculation is very simple, doesn't require a calculator. 2 times 0.9 is 1.8. 6 times 3.02 is 18.12. And then subtract 22 from that. You could do that in your head almost. Well, how close was this approximation? Well, if we go back to the original function that we have here, actually this equation right here, we could solve this for z pretty easily. We'd have 1/4 z squared equals 11 minus x squared minus y squared, and then you could solve that and get that z is minus the square root of 44 minus 4x squared minus 4y squared. We know what x and y are from this question that we're asking over here, so we'll plug those in. 0.9 here, 3.15 squared for y squared here, and for this you would need a calculator. Multiplying, squaring this, and squaring this are not too hard by hand, but then taking the square root of the whole thing, well, that probably would require us to use a calculator, and we'll get that z in our approximation is minus 2.0684. So if you look at the value of z that we had up here from our tangent line approximation, minus 2.08, and a more exact calculation, a closer, more accurate calculation down here using the original function gave us minus 2.0684. Those are pretty close together. This rounds off to minus 2.07, I guess, instead of 2.08, but that's pretty close. So I think we can be pretty happy with that result. The delta x and delta y that we used were sufficiently close to 0, so the approximation gave us a pretty accurate result. Let's look at a slightly different problem. Let's approximate f of x, y, z using our tangent plane approximation. So here's the problem. Let's let f of x, y, z be x squared plus y squared plus 1/4 z squared. We've seen that function before. And we note that f of 1, 3 minus 2 is 11. That didn't change. And let's approximate f of 0.953 minus 1.99. So what we'll do is, instead of plugging these numbers into this function up here, we'll plug these into the tangent line approximation of that function. So, part B, we'll use a calculator to evaluate f of this up here so that we can see how close our tangent line approximation was. So here's our solution. First of all, this part looks about the same as we had before. X squared plus y squared plus 1/4 z squared equals 11. This is our f of xyz right here. The gradient of f at 1, 3, minus 2 is still 2, 6, minus 1. So now we do something different from this point on. F of 0.95, 3, and minus 1.99 is f of 1, 3, minus 2. We know the value of f at that. It's 11, isn't it? Plus the gradient of f at 1, 3, minus 2 times, and now we have x minus x naught, y minus y naught, z minus z naught here. 0.95 minus 1, 3 minus 3, which is 0, minus 1.99 plus 2. And so what we have then is 11, which is this number right here, plus this vector, which was the gradient of f at 1, 3, minus 2, dotted with this vector, which is minus 0.05, 0, and 0.01. So we get the 11, and then we get 2 times minus 0.05, plus 6 times 0, plus minus 1 times 0.01. And that's what we have right here. So this we can calculate pretty easily. We have 11, and then here we have minus 0.1, plus 0, and here we have minus 0.01, and those add up to 10.89. So our tangent line approximation of f of these numbers is 10.89. Now, let's use a calculator to get a perhaps more precise, more accurate value of f at that point. And we'll do that using MatLab or Octave. We'll let x be 0.95, which is what we have up here. Y will be 3, which is what y is here. Z is minus 1.99, which is this. And then we'll calculate x squared plus y squared plus 1/4 z squared, which is f of x, y, z for those particular values of x, y, and z. And the answer, according to MatLab, excuse me, is 10.893, which is quite close to our approximation using the tangent plane approximation. So a pretty good result, and that's not too surprising because we didn't move very far away from the point 132. We moved the x value from 1 to 0.95. We didn't move the 3 value at all. It stayed 3. And instead of minus 2 here, we had minus 1.99. So these values of z, x, y, and z are very close to the values of x, y, and z we have here. And so we would expect our answer to be pretty close to 11. And we got 10.89, which is pretty close to 11. Our exact calculation, 10.893, obviously is even closer to 11. This was calculated in Octave or MATLAB using a format short. So it only gave us a few decimal places. If we put a command in here, format long, then we could have gotten more digits for our final answer over here. But in any case, we see that the approximation was quite good. Let's use MATLAB, the programming language MATLAB, or almost equivalently Octave, to do the following. Let's plot the ellipsoid x squared plus y squared plus 1/4 z squared equals 11, which looks like this ellipsoid right here. The gradient vector at the point 1, 3, minus 2, which is on that ellipsoid. 1, 3, minus 2 is right about here, and this happens to be the gradient vector there. And also, let's plot the tangent plane to this surface, at 1, 3, minus 2. And this is the tangent plane from some angle given to us right here. So what we want to do is to see how we can use MATLAB or Octave graphics to produce a figure similar to this one. Before we write the program, let's notice the following fact that we'll use in the program. If I look at the equation x squared plus y squared plus 1/4 z squared equals 11, and if I divide both sides of this equation by 11, which is the same as the square root of 11 squared, this equation will transform into this one, x squared over the square root of 11 squared plus y squared over the square root of 11 squared plus z squared over 2 square root of 11 quantity squared equals 1. We'll be using this equation in our MATLAB program. So let's take a look at the program. First, between percent left brace and percent right brace, we have a comment telling us what this program should do. And then the executable code starts down here. CLC is to clear the command window, close all closes all figures, and clear clears the workspace of any variables that might be out there. We like to put clear in here because if we ran another MATLAB program before this one, those variables might still exist and who knows, might interfere with what we're trying to do. So it's best to get rid of them. We'll let a be square root of 11, let b be 2 times the square root of 11, because we're looking at x squared over a squared plus y squared over a squared plus z squared over b squared equals 11, and we're going to do some division here, I guess. And so let's see what happens here. First, I'll let the variable phi have the following array. It goes from minus pi to pi in steps of pi over 25, increments of pi over 25. Similarly, for theta, we'll let it range from minus pi over 2 to pi over 2 with steps of pi over 25. Then we'll compute a mesh grid using lowercase phi and theta, and we'll store the results in capital phi and capital theta. And then for each phi and theta value, let's find the rectangular xyz on the ellipsoid. Maybe I should have in this comment capitalized the phi and theta here. So in any case, we have x is a cosine phi times cosine theta. Notice I used a dot asterisk for array multiplication. Y equals a times sine phi times cosine theta, and z equals b times sine theta. So by the time we finish this, multiplying arrays together, cosine of one array times cosine of another array, we have all of the data stored so that we can sketch the surface. So now we can use a surf plot to plot that surface, and we'll say that r equals surf of xyz, which we just defined down here. These are lists, and hold on. So when this is executed, we have our surface plotted. So now let's work around a normal vector to that surface at that point 1, 3, minus 2. We had calculated this before, I guess. We'll let u, v, and w be 2, 6, and minus 1. Those were the components of the gradient vector to our function that defined the surface at this point 1, 3, minus 2. And so now we'll use the MATLAB or Octave quiver command to draw the normal vector, a little arrow in our drawing. And we're going to draw it at the point 1, 3, minus 2. Since we're doing a three-dimensional version of an arrow, we're doing it in 3 space, we'll have to use the MATLAB or Octave function quiver 3. So h will be equal to quiver 3, and of 1, 3, minus 2, that's where the arrow starts, and then u, v, and w tells us the direction of the vector given by these components, which were the gradient of our function. I'll set the color to red for that quiver 3. I'll set for this h, which happens to be the quiver 3, a handle for that quiver 3. The maximum head size I'm going to let be 0.1, 0.1. We could put other numbers here too. 0.2 would give us more of an arrowhead, a larger arrowhead on our quiver, but this seems to be a pretty good one for our drawing. I'm going to let the axis in the x direction go from -8 to 8, in the y direction -8 to 8, and in the z direction -8 to 8. So after these are executed, we will have drawn the gradient vector. Also, let's plot the tangent plane. So let's let x be the following one-dimensional array. X equals linspace from -7 to 7, 32 steps, equal steps between here and here. Y will be similar, and then xy will be meshgrid of xy. Z will be 2 times x plus 6 times y minus 22. That's a capital Z, notice. And so then we're going to surf x, y, and z, and we're also going to plot the point 1, 3, minus 2, so we can see where that point is, hopefully, as a red asterisk, and then hold off. So what we did was we turned hold on way up here. We did plotting of 3 different objects, and then hold off. That ensures that we'll have all 3 of these graphical objects on the same axes, on the same plot. So, excuse me, let's look at a summary of what we have done in this video. We saw once again what the equations of a plane are. Here are 2 versions of it, where A, B, C is a 3-dimensional vector of constants. We defined what it means for a function to be differentiable at a point. We saw that a differentiable function has a tangent plane given by this type of equation, and in this equation we're assuming that our function capital F is differentiable at the point x0, y0, z0. So for an approximation for F, we would have that F of x0 plus delta x, y0 plus delta y, z0 plus delta z is equal to F at x0, y0, z0 plus the partial of F with respect to x at that point times delta x plus the partial of F with respect to y, the partial derivative of F with respect to y at that point x0, y0, z0 times delta y plus the partial derivative of F with respect to z at x0, y0, z0 times delta z. We could rewrite this letting x naught plus delta x be x, y naught plus delta y be y, and z naught plus delta z just be z. And so then we could write f of x, y, z is f of x naught, y naught, z naught, which is the same thing we have here. And then the rest of the formula looks similar to what we had up here. For a delta x, we have x minus x naught. For delta y, we have y minus y naught. And for a delta z, we have z minus z naught. I hope that you enjoyed this video. Please stay tuned for more to come.